Good morning, right. So, this is a rather simplistic way of doing things, and depends on so many things, like more often than not people may not be able to express their model behavior exactly like this, or may not be exactly able to give a reference model. So, such a simple procedure may not always be applicable, but what people do is that they do state certain, rather than stating a complete reference model, they often state some behavioral parameters of that reference model. For example, they can state that in the step response of the closed loop model, I want an overshoot which is generally stated as lower than something, maybe I want less than 10% overshoot, or you can say that I want less than so many seconds or minutes of rise time, which means that if I make a step change, it will quickly rise to that value. He may say that I want less than so much of settling time, which means that after the settling time, we will get nearly zero error. Or he can say, sometimes he can say that I want a certain amount of decay ratio. Now, what is decay ratio? Decay ratio is, so you see that if you have a step response, typical step response, closed loop plants are typically exhibit an underdamped response. So, our requirements may be based on terms of the overshoot, this is the first one. It may be based on some 10% to 90% rise time, which is this time. It may be based on a settling time, which is this time. Or it may be based on a decay ratio, which says that what is the ratio of the first overshoot to the second overshoot, that is this divided by this, second overshoot by first overshoot. Now, if the decay ratio is small, it means that even if you have a even if you have a first overshoot which is slightly large, but it quickly comes down. So, the ratio of second to first will be, let us say, if you require 25%, then it will be 1/4, then third to second will again be 1/4. So, which means that your error is rapidly converging to 0. So, in some sense it is good. So, you see that such things are often required. Otherwise, in various other controller designs, obviously stability is a consideration, and we have our well known gain margins and phase margins, which are basically protections that the loop will not oscillate even if the process gain changes by little bit, or the overall loop phase changes by little bit, because process models based on which we are going to calculate the controllers, they will not be exact. So, these are some of the common simple response parameters and stability parameters which are often considered in designing controller settings. So, let's see how. So, one example. For example, suppose I have a plant which is Kp by 1 plus STP. I am considering very simple examples. If you have more complicated examples, the solution process becomes more complicated, and you need numerical procedures for actually solving out. But in essence, the method remains the same. And suppose I am considering a PI controller. I have already selected a PI controller, and I want to set the value of Kc and Ti. Suppose my criterion is quarter decay ratio, that means the second overshoot, the ratio of the second overshoot to the first overshoot will be 0.25, will be right. So, it turns out that decay ratio will be given, is actually given by this formula. So, this value should be less than 0.25, which means that we can just simplify matters of solutions by saying that the log of the decay ratio, we can take log on this side. So, we can have ln of the decay ratio is approximately equal to, this is gone, then approximately equal to this, or equal to, let us say. So, now so this I want to be equal to 1/4. right. So this becomes equal to ln of 1/4. Now what should be the value? So what I have to find out essentially is what should be the value of this zeta such that this function evaluates to be less than ln 1/4. Now what is zeta? So if I compute GGC by 1 plus GGC, then I will get in the denominator I will get some parameter in the form s square plus twice zeta omega n s plus omega n square. So it will turn out that omega n is also a function of these parameters, and zeta is also another function of these parameters. So this zeta is going to be some function of Kc and Ti. So that's what we are saying, that if we try to solve this, finally it turns out to be an equation of the type, we'll get an equation f of function of Kc and Ti is equal to ln of 1/4. So now we got one equation, but we need to find out two parameters. So obviously we cannot find a unique solution, there are actually many solutions. So which means that to be able to find unique solutions, we need to have some other criterion. So we can actually accommodate some other criterion. For example, if we consider in addition, so we have another criteria needed to determine Kc and I am sorry about this one. So I need another criteria, and then suppose I could use various kinds of criteria. So for example, one criteria I could choose is that smallest overshoot. I will choose that value of Kc which for a given value of T1 gives me the minimum overshoot. So I not only want that the overshoots will decay fast, I also want the first overshoot to be small, so that I will reach settling time will become even smaller, right. So if I want to do that, then I will take the overshoot function and then I will differentiate it with respect to Kc and then set it to 0. That will give me another equation. So now I have two equations and I have two unknowns. So now I can solve for Kc and Ti. So you see, so it is essentially stating properties of the closed loop function, then expressing them in terms of the unknowns, that is the gain various times of the PID setting, and then solving those equations. This is the essential procedure. So these are direct solving procedures, and now we see that it's not always that we are going to state them in terms of this kind of overshoot or settling time or decay ratio. There are various other ways that we can specify control parameter performance, and essentially numerically we have to solve out the various parameters. These are generally not able, we will not be able to solve them analytically in such cases, excepting some rare cases. For example, we can select that the integral square error, that is after a step response is generated, there will be error. So if I integrate the error will eventually come to 0. So if I integrate the error, the square of error, then I should choose such values of gain such that this function is going to be the least. Now why should I choose a square of error? Why not cube of error? Why not whole to the power 4 of error? Generally square of error is actually very popular because of two things. First thing is that in square of error we are able to weight higher errors. That is, we are saying that if you commit an error of 2, you are 4 times better than if you commit an error of 4. So double errors, if the error magnitude goes double, then the control performance criterion which is to be minimized goes 4 times up. If you go 3 times, it will go 9 times up, which means that we are heavily penalizing large errors. So when we want to heavily penalize large errors, we generally choose powers of E, and square is chosen because the square criteria generally leads to very nice solution equations because by differentiating square you get linear equations which are very easy to solve. But in some cases, as we have seen that in the case of the pH control of the water discharge system, we may be interested in, and if we are not interested in penalizing high errors too much, then we may choose integral of absolute error. Sometimes we may like that, fine, let there be error initially, but let the error not persist. So, in which case I can choose what is known as an integral time absolute error, where you can see that if an error occurs earlier after the step change, it is not penalized so heavily, but if it occurs later as time goes high, the same amount of error is more and more heavily penalized. So, what we want is that if you want to have errors, even large errors, have them in the beginning, but after the step change within certain times the errors must quickly converge to 0. So, the errors must not persist for long times. So, this is what we are saying. So, that is what this says, that the integral square error strongly suppresses large errors. The integral absolute errors are better for small errors, because in small errors E squared t becomes even smaller. So, the small errors are not penalized. And in ITAE what we want is that we want that quickly errors converge. So, we want to suppress long persistence of errors. So, for example, if you took a typical, this is a typical waveform, that if you took a control loop which is designed based on ITAE, it may so happen that you will initially get a high overshoot, but it will probably die down faster, because that is what is penalized heavily. On the other hand, if you take an IAE, if you compare between IAE and IAC, you will find that in IAC error magnitudes are going to be less than IAE, because in IAC bigger errors are actually heavily penalized. So, the error will not rise very much, but it may not fall so fast also. That is, when it reaches a low level, it may persist for long times. So, this is what happens if you, so depending on your choice of your performance criterion, you can get different kinds of transient performance in the loop. So, in the remark we are saying that sometimes we have more than one criterion, sometimes criterion may be conflicting also. If you want to cut down on rise time, you generally have to increase the gain too much. If you increase the gain very heavily, then you tend to have very large overshoots. So, having a small rise time and having a small overshoot are generally conflicting criteria. So, you have to strike a compromise. In many cases what will happen is that your criteria may be stated in terms of inequalities. So, you actually have a feasible region in which you can operate, and in many cases, so when you have complex processes and you have complex performance criterion, the calculation of the gain may require large amounts of numerical trial and error over using sophisticated optimization algorithms which search for a good value of the parameters over some feasible space, and therefore you need software, and various kinds of tuning software actually sell from the manufacturers. Now, all these that we have so far talked about generally assumes that that model forms are available, but in many cases you may not exactly be able to obtain the form of a model, and then you must model the process using some simple model structure and based on some experiments. So, you actually perform an experiment, see the response, measure certain properties of that response, and then design your controller based on that, right. So, typically you can have either open loop response, open loop experiments, or you can have closed loop experiments. So, we are going to look at these two. So, for example, a typical very popular way of open loop experimentation is the reaction curve. That is, you take the open loop plant, which is typically of this, assumed to be of this shape, but it is not directly in the experimentation. This form is not used. So, you do a do a step response experiment. So the output is going to rise. This is for the open loop plant. So the output is going to rise like this. So now numerically you find out that typically in this model, if you consider the step response of this model, then this step response will actually rise after a time Td because of this e to the power minus std term, and then it will rise just like a first order system k by 1 plus s tau. So the slope of this line, is going to be given by k by, that is m is equal to k by tau, or rather tau is equal to k by m. So perform an experiment, assume that the plant is of this form, which is a reasonable approximation for actually many plants, and then measure out what is the value of Td and then what is the value of, what is the slope m, and based on the slope m and the final settling value, which will give you the value of k. So now after the experiment, you know this Td, you know this k, and you know this m. So now you then based on this, people have various kinds of empirical rules. Empirical rules means process control experts have actually done through their experience by many simulation and experiments, actual experiments, they have given some thumb rules that if you find that k is of so much value and m is of so much value and Td is of so much value, then use, if you are using a P controller, use this value of gain. If you are using a PI controller, use this value of k and this value of Ti. So there are certain rules which are not analytically derived but are empirically derived. So entirely means just by doing experimentation from experiments, they cannot be explained. So very famous rules which are Ziegler-Nichols. So the Ziegler-Nichols tuning rule says that if you do this experiment and if you are designing a PI controller, then the value of the gain Kp should be this much. So you see in terms of Td and m, and the value of Ti should be given in terms of Td. This is what Ziegler and Nichols found works well. Now obviously it will not work well everywhere. So various people will say various, so we have various other kinds of rules also. For example, we can have another rule which is known as the Cohen and Cohn rule, which looks like this. So you see that they are actually fairly close. Only thing is that Ziegler and Nichols said that Kp should be this much. Now Cohen and Kuhn are actually adding another term. So here also you see that in case of he is adding, apart from this Td, he is adding a factor here, right. So you see that various kinds of empirical rules are given and then you can apply. Now actually what happens, one must realize this, that actually what is going to happen is that, say, look at this, that you are looking for, you are searching for some good parameters, let's say in the Kp, Td and Ti space, right. Now suppose the real best value of parameter actually lies here. So now you can exhaustively search the space and maybe finally you will actually locate that is the best value of parameters, which is very expensive. So the idea is that if you can search, by some simple rule, if you can locate a value which is likely to be very close to the real true optimal value, then your search becomes easier. You actually quickly converge on to the optimal. While if you don't have the benefit of this rule, which is given by this Ziegler-Nichols, Cohen-Kuhn kind of rules, then you may start search from here and then after long amount of search you may reach here. So it is basically, these rules should be taken in that spirit that they generally give you a good first guess for the values, and then you may have to do some amount of tuning to actually be able to get the real good parameters, controller parameters for your process, right. So an overall assessment of this open loop process is that you need only a single experiment, just once give a step input and collect the values. no trial and error is needed, and for some processes loop cannot be opened. This is a big problem that we want to do an open loop experiment. Now some processes are there already in closed loop. Now you cannot open them. Nobody will allow you to open the loop and do an open loop experiment. So in such cases this is not applicable, and sometimes determining these slopes etc. can be actually very difficult, especially when you have noise. When you have noise, finding numerically the slope from data can be very complicated, and you have to use some good approximation procedures. And finally note that this procedure is actually applicable only for over-damped processes, not for under-damped processes. So you cannot take an under-damped, open loop under-damped process and then use this procedure, although you may be able to find out some value of K, TD and M. So we need a closed loop procedure. And the closed loop procedure goes like this. It is essentially an iterative procedure, that is, it involves trial and error. So what it does is that first get the loop in a stable condition, probably the loop is already in a stable condition operating. Then minimize action of integral and derivative modes, reduce those integral and derivative gains, if necessary reduce the Kp also, so that the loop is stable. Now make a step change in the set point, right? So if you make a step change in the set point, so you make a step change in the set point. So the process loop rises and it dies down. If it dies down, then if the cycle damps out, then you reduce PB. Reduce PB means increase the gain. So if you increase the gain, your gain margin will reduce, which means that the process will be closer to an oscillation. So maybe when you reduce the gain, next time you give another step. So you go to step 3 and then make another step change, maybe in the negative direction. So then it may happen that this loop will tend to persist for longer time. Still it damps out. So still it damps out, again go to step 3 and then reduce gain little bit and make a step change in set point. So go on doing this till the loop oscillates. If the measurement cycles with constant period and amplitude, note this period tau and the PV value, that is the gain which has made the plant oscillate. This is called the ultimate gain, right? So now you have got two values. One is this PB star, which is the ultimate gain, and another is the period tau naught. So now based on these there are again empirical formulae. So for example, Ziegler-Nichols says that if you have found a particular value of PV star and found a particular value of tau naught, then for a PI control, set the proportional band value as 2.2 times this value and set the TI as this value. Again empirical, purely empirical, found so called by experiments. Similarly, some other process control expert, Shinsky, says that no, choose these two values of gain. So obviously you are going to have difference in these properties. For example, here you have a larger gain and here you have a larger time constant too. Here you have a smaller gain, here you have here you have a smaller gain and you have a smaller time constant. Here you have a larger gain and you have a larger time constant, right? Larger gain and a smaller time constant. So you will get different properties. So what is the assessment of these closed loop methods? That some trial and error is needed, and often the settings obtained, so as I have already told, that the settings obtained are to be treated as good first estimates, and further trial and error, after around that you may like to tune little bit and see whether you are getting still better performance, then you should select those values. Now for some, it so happens that this cycling, when you want to make the loop cycle by continuously increasing PV, the cycling amplitude, that is the amplitude of the cycle, may increase. It is actually not in your control. When a process oscillates, its cycling amplitude and period are actually not in your control. So now, but then that may be disastrous, because a process may not be allowed to cycle with a very large amplitude. So then what are you going to do? So in such a case, there is a nice procedure which says that set up the control loop like this. So you have the normal PID controller and you have a relay with hysteresis here. So what does it mean? That if the error goes positive, then the relay will switch in one direction. If it is negative, it will switch in the other direction. So now what will happen is that because of this relay, if you now flick the switch and then try to control the plant with this relay, then what will happen is that the relay will continuously toggle. So the relay will give you an oscillating input. So what will happen is that the plant will actually oscillate. Immediately it will start oscillating. There will be no trial and error needed. And the amplitude of oscillation can now be controlled by the properties of the relay. So now you have got a nice situation where the oscillation can be directly induced by the relay without trial and error, and its amplitude can be controlled. So you can induce a small oscillation, and then note the period of this oscillation. And it turns out by an analysis which is called the describing function analysis in nonlinear control, that if you have an oscillation of this kind in the process, which is of amplitude A, which can be controlled, and if the relay switchings are of amplitude 2D, then the ultimate gain which you wanted to find out to be able to apply the closed loop tuning formulae can be given by this formula. So you see, you are still finding out that same gain PB star, but now using an experimental procedure which lets you set up an oscillation at one shot of a controllable amplitude. So that is the big advantage, and then now you can easily apply those formulae and then get the gain. And it so happens that people have actually implemented this commercially in the PID controller, so that whenever the operator feels that the process needs to be retuned, then the process can be momentarily flicked onto the relay and immediately an oscillation will be set up, and then by noting the amplitude of oscillation and the period of oscillation, the gains can be set up in very quickly. So no separate experimentation necessary, and then automatically the controller can be tuned just by the flick of a push button. Therefore it is called auto tuning, right. So here the whole tuning process has been automated. So this is the end of our lesson, and what we have basically reviewed are the various performance criteria for control loops. Then we saw a method of direct computation of controller settings based on a process model, open loop plant model, and a reference model. Then we found out some empirical tuning rules which are based on open loop and closed loop experiments that you can perform on the plant. And finally we saw a procedure called auto tuning, where we could quickly and automatically do an experiment and find out the controller settings. So some of the points to ponder for you is that you can try to find out in what situations PI and PID controllers are to be used. All the answers are in this lecture only, and you can try to find out your own examples of processes. And then under what conditions one can apply a direct synthesis procedure, let us say in your application processes, whether you can apply or not, or if you can apply, why you can apply or why you cannot apply, all these things. You can also cite two advantages and disadvantages of open loop method against the closed loop method. And finally, you can find under what situation an auto tuning feature will be needed and how is it achieved, how an auto tuning is achieved. One procedure is already given in the lecture. So here we end. Thank you very much.